So today we'll be discussing the probability theory. So the slides were prepared by Zara and Jeremy. Okay, let's start. So can anyone tell me what a sample space is? Anyone? So a sample space is the set of like all possible outcomes of an event. So for instance, like if I'm tossing two coins, so it'll be like head, 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 tail, tail, head, and tail, tail. So we define events that belong to the sample space. So say if I want to say like the first toss of the coin should be a head, so these are the possible outcomes. So basically we define the event space F, and the probability is a function from this event space F to the set of real numbers. So as we know, the probability of any event will be greater than or equal to 0 for all A belonging to the event space, and probability of the sample space will be 1. So if A1 and A2, if we have like multiple events that are happening and they are disjoint, we can find the total probability by just summing the individual probabilities. Coming to conditional probability and independence, let's say we have an event B, assuming that the probability of B is non-zero. We can define that the probability of event A, given that B has already happened, as probability of A intersection B divided by probability of B. So we can prove the left hand. We can show the left hand side and the right hand side by taking the same example that we've been talking about. So if I'm tossing two coins, so say event A is so we have to find the probability of A given B. So let's define event A and B as follows. So let's define B that the first toss resulted in a head, and A is defined as probability of a head occurring. So how will we define probability of A given that B has already occurred? So when we say the first toss was a head, so we'll consider these two outcomes, right? So can anyone tell me what will be the probability of A given that B has already happened? What? Will it be 1? Why will it be 1? Can you explain your answer?
Because if the first toss is head, then the head has already occurred.
Yeah, sorry, let me define this on the second toss. Okay. Yeah, what will be the probability be? Yeah, exactly, it's half. So how we are thinking of this is like, okay, so we basically have to consider these two options, and the probability of the second half is like 1 by 2 of these two. So how will we define, okay, so that will be, so in this case, the probability of A intersection B sorry for the distraction. Okay. So in this case, how will we define the probability of A intersection B? Like what will be the probability that both of them are heads? 1 by 4, right? So, and the probability of B that the first toss is a head is already 1 by 2, right? So we get the probability will be 1 by 2. So we can go either way in this approach. So okay. So can anyone tell me what will be the probability of A intersection B given that A and B are independent? I want this term I want the probability of A intersection B, given that A and B are independent. Yeah. Exactly. So it will be probability of A times probability of B. So when we divide by, so we just get probability of A, given that B has already happened, will simply be equal to probability of A in case they're independent. And that makes sense from our definition as well, right? Okay. So, okay. So, can anyone tell me what a random variable is? Anyone? Guesses? Okay. So, a random variable is basically when we map the outcome of a random process to a number, right? So, for instance, we usually denote the random variables by a capital letter. So, I can say as if like, so x will be 1 if I get a head and 0 if it's a tail. Okay. So, do you know like what will be the sum of the random variables? Like, does it have to be 1? Or can I just give it this a value like, say 123, and this could be like say 0? Would it be like, is this allowed or not? Yes or no?
Yes.
Yes, this is allowed. So, okay. So, can anyone give me other examples of random variables, and why do you think they are important? So, another example that I can think of is like if you're in a library, right? And you're picking up like one of the, like say the first student that comes up with a book. So you're counting say the number of pages or other such things. So that will be, so the number of pages in this case will be a random variable, right? So it makes a little more sense to us than like thinking of probabilities all the time. And the another reason why we use random variables is, say for instance, I have, so say I have a dice. Right, and so I want to like sum the number, like sum all the faces on the dice, right? So, so one thing I can say is like, okay, if I want to sum all these up and I want to see, okay, if it is like say less than equal to 20, so how will I write the probability of this? Can anyone speak it out? Like, how will I write the probability? I'll just say probability of sum of all edges of dice is less than equal to 20, right? This is a long notation. Like, why do you want to write so much, right? So we can just define the random variable in the beginning and say like what purpose we want to solve by that, and like just use probability of x less than equal to 20. So it simplifies our mathematical notation as well. Okay. So now I'll be handing over the mic to Andy. He'll be talking more about random variables and probability functions.
Okay.
So we can just skip this. Okay, let me just explain this. So, so a random variable can be considered as a function from the sample space to the set of real numbers. So for instance, like if I'm tossing 10 different coins, so say this will be one of the possible outcomes in the sample space, right? So if I want to say, okay, what will be the, so if I'm defining x as the number of heads that come in my outcome, so in this, the value of x of omega naught will be 5. Similarly, I can define number of tosses until tails. So in this case, it's 4, right? So, okay, just one last question from my end. So like, if like I'm defining the value of x to be like all possible values for x of the sample space, Can you tell me what are the possible values of x in this case when I define x to be the number of heads? Like what possible values can it take, like considering all the outcomes? Exactly. Nice. I wish I had a chocolate to give it to you. Okay. Got it.
Okay. Okay. So now that we talked a little bit about random variables, we're going to talk a little bit about the difference between discrete and continuous random variables. So a discrete random variable is a random variable whose values are countable. So in this case, we can think of it as like students' letter grades, or the number of marbles in a jar, or in Jaspreet's case, the number of heads or tails that we get from flipping a coin. And ooh, so loud. Let's put it down here. So we can break down the notation. What this notation means is the probability of the discrete random variable taking on a value k. But it's got this little wonky notation, so I'm going to break that down a bit over here. Sorry, this one's not working very well. Switch. Thanks. Test? Okay. So. Okay, so we write down that the probability, or that the random variable takes on a value k, is equivalent to the probability of a certain random outcome, given that the outcome with the function, the random variable function, takes on a value k. So in this instance, we talked about how the state space is omega, right? So x of omega is all the possible values that the random variable took on. So when we think of a coin, two coins flips, we can think of it as taking on either the possibilities heads, head tails, tails heads, and tails. So in this case, it's taking the state space mapping to all the possible states are these four states. So what we're saying right here is basically, what is the probability that a certain outcome, omega, given that our mapping of this outcome is equal to some real number that we understand. So in this case, if I ask what the probability that we get two heads is, this is equivalent to saying, what is the probability that our random variable takes on the value 2. So it's a little technical jargon, but we write this shorthand as probability of x equals k. So now we're going to talk a little bit about the probability mass function. The probability mass function is the function that gives the probability of a discrete random variable that is equal to some value. In this case, the probability mass function is exactly equal to that probability that we just described. Can anyone tell me what the sum of all the probability mass function over all values over the state space would be? 1. Yes. So that makes sense because it's kind of like conservation of mass. We want all the possible outcomes of x to be probability 1. As we talked about, as Jaspreet talked about, the probability of a state space equals 1. So analogous to the discrete random variable case, we have the continuous random variable. And in this case, the continuous random variable is very similar in that we get a certain state space and we map it. So we map, in this case, an interval instead of a value. Does anyone know why we map an interval instead of a real number?
Because the probability of a single number would be infinite.
Yes, exactly. So for continuous random variables, the probability that the random variable takes on a constant or a certain value, so in this case, for a continuous random variable, probability of x equaling a constant does not equal the probability density function at that value because we have infinitesimally small probabilities. To make more sense of that, if we think about continuous random variables as, let's say, the distribution of the heights of students, we can never say for a fact that someone is exactly 5 feet tall. They're going to be 5 point something feet tall, or something very, very close to a certain value, but we'll never actually take on that value. So that's why we encapsulate probabilities with continuous random variables in intervals. And analogous to the probability mass function, we have the probability density function, which is the continuous form and has many of the same features. I'll talk a little bit about the cumulative distribution function, but for now, the probability density function is a derivative of the cumulative distribution function, as I talked about. And just like the probability mass function, does anyone know what this integral evaluates to? 1. Perfect. So now talking a little bit about the cumulative distribution function. Does anyone have any questions? Okay. Talking a little bit about the cumulative distribution function. Now the cumulative distribution function is essentially an integral of the probability density function. This cumulative distribution function is a function that takes on a real value and finds out the probability that x, the random variable, is less than that certain real value. So in this case, the cumulative distribution function at a real number x is equal to the probability that x is less than or equal to that x, big X. Here's the CDF of a normal distribution. If I draw out the normal distribution, and I'm going to put it on the same scale as this one. So we have a normal distribution, and if we notice that we integrate this function, we get exactly that function. So can anyone tell me what, if I took x to be 0, what the probability of x being greater or equal to 0 be? 1/2. Even though we have the CDF equaling to probability of x less than or equal to x, how can we transform it so that we make sense of this upper probability? How can we turn this inequality the other way around? Yeah, exactly. So this is exactly equal to 1 minus the probability of x greater or equal to x. So looking at this graph, we can see that if I put x to be 1, what would be the rough area of this right tail? Which in CDF form I could write as this, greater or equal to 1. Just using that graph. So if I trace up the 1 up to the graph, we'll see that roughly 0.7 or 0.7% of the probability is to the left. So this right tail will be 1 minus 0.7, and so our CDF will take, or our right tail will take on a value of 0.3. So now we're going to talk a little bit about expected value and variance. The expected value is a function that more or less tells us the long-run average value of a random variable, whether it's discrete or continuous. So in this case, we write out the definition. It's the expected value of a function of x. So g can be any well-defined function. The expected value of that g of x is exactly equal to g of x times the probability mass function with a discrete case over all the state spaces. So what does that mean? So let's think back to the coin flip example. A Bernoulli, let's say X is distributed Bernoulli with probability P. And we notice that the probability mass function for this is P if X takes on a value 0, and 1 minus P if X is 1, which is, backwards. Which is exactly telling us the probability of a coin flip. In this case, if we wanted to take the expected value of X, how can we compute this expected value, given that some equation that and g of x is just x? How can we compute that expected value? So to compute this expected value, we can just break apart that formula. So all of our state space is 0 and 1. So really we'll only have 2 terms in this sum. And we see that g of x is just x. So x, we're going to be summing over 0. The state space is 0 and 1. X times a probability density function. So this breaks down to 1, which is when the state space is 1 times the probability at 1, and plus the state space is 0 times the probability that that occurs, which is 1 minus p. So we see this boils down to p. So our expected value for a Bernoulli random variable is just p. So I'm going to give you guys a little harder question, and I want you guys to work it out and talk to your neighbors about it. So a Poisson PDF and PMF has this distribution. What would be the expected value, and g of x is just x? Can you guys work out the expected value of x given this Poisson distribution? This is a Poisson with rate lambda. And I'll give you guys about 1 or 2 minutes to try to work this out. Sorry, I forgot to write. X is greater or equal to 0. Okay. Has anyone come to an answer for this? This one's a bit tricky. Okay, I'm going to walk through this quick example, and then I'll move on to variance. So for this, we can write out the exact definition for expected value. So in this case, the state space of our discrete random variable for Poisson is from 0 all the way to infinity, because we're just counting the number of rare events, and counting is positive. So we iterate from 0 to infinity for x, and x e to the negative lambda, lambda x over x factorial. And so we notice that the bottom terms can cancel out. And so this, I'll write it up here, reduces to x is equal to 0, e to the negative lambda, lambda x over x minus 1 factorial, because we cancel out with one of the terms of factorial. We factor out, or I guess I should, before I do this, we notice that x at 0, this 0 just cancels out all the terms. So this is actually equivalent to starting to index from 1. Because 0 times whatever is just going to cancel out all the other terms. So I'm going to start indexing by 1 from here. And then I factor out an e to the lambda e to the negative lambda. And I take the sum from x1 to infinity of e to the lambda to the x minus 1, because I factored out a lambda, over x minus 1 factorial. And then we notice that this term is exactly the series expansion of the Taylor series expansion of e to the x. So in this case, it's not e to the x, it's e to the lambda. So these two terms cancel out, and we see that our expected value of a Poisson is just lambda. Any questions? So yeah, we'll be moving on to, there's also the expected value for continuous random variables, but it's computed the exact same way, except you use integrals instead of summations. Now we're going to talk a little bit about variance. The variance is essentially trying to understand, we're trying to capture how much does the random variable deviate from its mean. So in this case, we take the expression right there, and it makes sense, right? We take essentially the residuals. We're taking the random value minus its expected sum and squaring it. So we're trying to get an idea of how far from the mean we are. And by linearity, it reduces to this. And you guys can go home and maybe work out a couple of examples for variance. And here are some couple of example distributions. So as you can see, the ones that we use a lot for this class are Gaussians, uniforms, and exponentials. Gaussians and exponentials typically because, as you guys saw in the lecture, that they're both part of the exponential family, and typically there's a lot of interesting stuff that you can do with exponential family models. And of course, I can extend all the random variables to their bivariate cases. In this case, we have the bivariate PMF and the bivariate PDF, which is essentially the 2D form of all the things that we just described. So in this case, we have a random variable x and a random variable y, and we can describe joint densities between these two phenomena. So for instance, if I had x is distributed exponentially with parameter lambda, and y is distributed exponentially with parameter lambda, then I can, and I say that the joint density between the two is equal to, or yeah, the joint density is equal to this. We can see that we get both the x and y components in this joint density. And you can take some time and derive some of the marginal PMFs, but you'll notice that this, if you take the integral of all of this, that you'll be able to factor out the y component and see that the integral converts back to the normal exponential PDF. And now we're going to talk about the Bayes theorem. I'm going to hand off this.
Hey, okay, let's continue on the Bayes theorem. Basically, what's the Bayes theorem? Bayes theorem saying that given a conditional probability of two events, how you can find the reverse conditional probability. So, for example, here, suppose y and x are two events, and you have access to the probability of the x given y. Also, you have access to the probability of the x and probability of the y. And also, you know that the probability of the y is not 0. What you want is that to find the probability of the y given x. Probability of the y and probability of the x are both marginal probability of the x and y. And depends on if your x and y are continuous random variables or discrete random variables. They can be either calculated from the p of the x or from the f of the x. F here is the PDF, probability density function. An example, suppose you have two chests. One is full of the gold coins, another is like half gold, half silver. You close your eyes and you randomly choose one of those chests and pick a coin. The coin is gold. What you want is that what's the probability that you choose, you have chosen the chest A. Do you mind to calculate it for me based on the Bayes rule? So remember, Bayes rule is saying the probability x given y equals to the probability y given x times probability of the x given probability of the y. Here, x is the event of choosing chest A. Y is the event of seeing a gold coin, right? What we want is that what's the probability of choosing chest A given that we already seen a gold coin, right? How many people say the answer is A? B? C? None of them? Okay, many people do not have any idea. So to calculate this one, according to the Bayes theorem, we can say this one equals to the probability of seeing a gold coin given we chose chest A times probability of choosing chest A over the probability of seeing a gold coin. Okay, so let's do it together. This one equals to this. What's the probability of seeing a gold coin given that we already choose the chest A? If you choose the chest A, what's the probability that the coin that you are taking out is a gold? 1. What's the probability that you choose chest A? you have two chests, right? And then you randomly pick one of them. What's the probability that you choose the chest A? Half, right? And now this part, the marginal probability, right? The probability of the seeing a gold coin equals to the probability that you choose chest A times the probability that see a gold coin given you chose chest A. I think you can see this part. Plus probability of choosing chest B times the probability of the seeing a gold coin given choosing the chest B, right? So the probability of the choosing chest A, as we said, is half, right? So it is like half times the probability that you choose a gold coin given that you already chose chest A. Chest A is 1, right? The probability of the choosing chest B is half. The probability that you choose a gold coin given that you already choose chest B is half, right? Because half is silver, half is gold, right? If you simplify this one, it will be 1/2 over 1/2 plus 1/4, which is 1/2 over 3/4, which is 2/3. So the answer is B. Is it clear? Cool. Independence. Independence is also one of the important properties of the random variables. Two random variables are independent if the happening of the one random variable doesn't have any effect on the other random variable, right? If two random variables are independent, then the joint probability of them can be expressed as the product of the probability of each of them. For example, here, x and y are two independent random variables. So the joint probability of the x and y equals to the product of the probability of the x and y. And also, if two random variables are independent, right, the conditional probability of them equals to the marginal probability of one of them. So here, the conditional probability of happening y given x is already happened is the probability of the y, right? Because x doesn't have any effect on the y. Also for the continuous, this one is for the discrete random variables. For the continuous random variable, you just need to replace p with the PDF. Example, suppose you have a spinner and it can have any number, 1, 2, 3, 4, between 1, 2, 3, 4, 5, 6, and 7. Also, you have a coin that can have tail or head, right? You spin this spinner and you toss this coin, right? So the question is that what's the probability that you see an odd number from the spinner and a head from the coin? As you see, these two random variables are completely independent, right? It doesn't matter if you see head or tail from the coin, or if you see an odd or even number from the spinner, right? So here, the joint probability of the x and y equals the product of the probability of the x and y, right? So here, for example, 1/2 is the probability that you see a tail, right? And 4/7 is the probability that you see an odd number, right? So here, the joint probability of the x and y is the product of the probability of the x and y.
But in this case, like x and y both have different sample spaces.
That's correct.
So they're always any event, like you take any event from x and any event from y, they're always going to be independent.
That's correct. Yes. I'm just saying that how it's like look like if you have two events that are independent from each other. Expectation. Expectation is the average, the weighted average of the possible outcome of a variable, right? Of a random variable. So, for example, we already mentioned if you have, if you have a die, and then you toss a die, the outcome can be any number from 0 to 6, right? The expectation of the random variable, suppose you have a die that can have any number from 0, 1, 2, 3, 4, 5, 6, and each of them, the probability of having each of them is 1 over 6, right? So the expectation of the x equals to summation of the product of each possible outcome and times the probability of that outcome, which is 0 times 1 over 6 plus 1 times 1 over 6 plus 2 times 1 over 6, right? If you have more than one random variable, for example, here you have two continuous random variables, the expectation can be expressed as the integral of the joint probability between these random variables times the function that you are trying to take the expectation from it. For example, look at this example. We want to find the expectation of the g of the x and y. G of the xy equals to 3x, right? And the joint probability of the x and y is 4xy. And you know that the x and y are two events that varies between 0 and 1. How you take the expectation? Expectation of the g of the xy equals to the integrate of these two random variables, 3x times 4xy, dx dy. Is it clear? Cool. Covariance. Covariance is also important. Basically, covariance is saying that how much changing one random variable can affect on another random variable, right? So if the covariance of the two random variables is 0, you can say that changing one random variable doesn't affect linearly on changing the other random variables, right? The covariance is mathematically expressed as this one. Covariance of the xy equals to expectation of the x minus expectation of the x times y minus expectation of the y. If you simplify and expand this equation, you can see that this one equals to expectation of the xy minus expectation of the x times expectation of the y. The important thing that you can see here is that if x and y are independent, then expectation of the xi equals to expectation of the x times expectation of the y, right? Why it is that? It's simple to see. So expectation of the xy equals to xy joint probability of the xy dx dy over x over y, right? But since x and y are two independent random variables, this guy can be reduced to f of the x times f of the y dx dy. It can be written as y f of the y dy times x f of the x dx, which is expectation of the x times expectation of the y, right? So if two random variables are independent, the expectation of the xi equals to expectation of the x times expectation of the y, right? So if you apply this one to the first equation, to this equation, it means that if two random variables are independent, the covariance of them is 0. But the other way is not true. It is possible that the covariance of the two random variables are 0, but they are not independent. This is coming from the fact that covariance shows how two random variables are linearly independent to each other, right? it is possible that two random variables are non-linearly dependent, which cause the covariance is 0, but they are not independent, right? Another important thing is this line. If you want to find the variance of a function of the random variables, it is not always necessary to have the expectation of all of them. For example, here, if you want to calculate the variance of the x plus y, as you know, it is equal to expectation of the x plus y squared minus expectation of the x plus y whole square, right? If you expand this one, you can see that this one will be reduced to the variance of the x plus variance of the y plus 2 covariance of the xy, right? So it means that to calculate the variance of the x plus y, you don't need to have the expectation of the x and expectation of the y, right? As long as you have the variance of the x and y and the covariance, that's fine. And also one important thing here is that do you know what's happened if you if you replace y here by x? What's happened? What's the covariance of the x and x? The x and x is the variance of the x. Okay, cool. Okay, another important topic is the multivariate Gaussian distribution that we use this concept very much in CS229. So basically, if you have a vector of the random variables that each of them is a Gaussian random variable, right? If you have a vector of them, then you call this vector a multivariate Gaussian distribution if each of these random variables itself is a normal distribution, right? So in this case, x is like a vector of the x1, x2 to xn, right? And each of them is like a normal has a normal distribution with a mean mu1 and then sigma the variance 1, right? x2 also has another Gaussian distribution with the mu2, z2, call it zx1, zx2, right? And then if you have a vector of them, then you can say x is a normal distribution with the mean is a vector of the mean of these random variables, which is mu1, mu2 to mu n, and sigma, right? And what is the sigma? Sigma is the covariance matrix between all of these random variables. So this is a symmetric matrix, right? Do you know what's the diagonal elements of the covariance? 1. Is it 1? Or is it variance? The diagonal elements of the covariance matrix is the variance of that specific element. So here it is zx1, zx2, right? Zx3. Because do you remember that sigma is the covariance of the x and y, right? So if x and y are both same thing, the covariance will change to the variance, right? So the diagonal elements are the variance of the random variables, and then non-diagonal elements of the covariance of the elements, right? And remember that the covariance is a symmetric matrix, meaning that these elements are all same, right? And also covariance is a positive definite matrix, right? Okay, so if you have this relation, then you can find the joint distribution of the multivariate Gaussian distribution, right? Replace it at this one. It looks like a bit complicated, but it's not. You can have it on your cheat sheet. So basically, you can see if you put n equals to the 1, it will reduce to the one-dimensional Gaussian distribution, right? If you put n equals to the 1, what happened? Suppose n equals to the 1, right? This one will be the probability of the x with mu, and here sigma x equals to 1 over 2 pi, 1 over 2 times sigma x, right? Because it's sigma x is square and then half, times exponential 2 sigma 2 x minus x minus mu x squared, right? Which is, you already know that this is the distribution of the one-dimensional Gaussian distribution, right? If you have 2, let's see what happens. If n equals to the 2, you can say the mu is, call it mu x, mu y, and then the covariance is like this, right? These elements are the variance of the x and the variance of the y. And suppose that the correlation between x and y is rho. Rho is the correlation between x and y. So you can write this covariance matrix as rho sigma x sigma y, rho sigma x sigma y. And as you see, this is symmetric, right? Then, if you want to apply this mu and sigma and n equals to 2 to that equation, you've already used to this one. The probability of the x and mu and sigma equals to 1, 2 pi, 2 over 2, right? And then if you want to find a determinant of the sigma square root, it will be sigma x, sigma y, 1 minus rho squared times exponential of the minus 1 over 2, 1 minus root rho 2, x minus mu x squared over 2 sigma x over sigma x squared plus y minus mu y squared over sigma y squared minus 2 rho x minus mu x, y minus mu y over sigma x, sigma y, right? How I got this one? If you do like the vector calculations between the covariance matrix, you can end up with this equation. But for the like more dimensions, you need to put the whole vectors, and you see that it will be reduced to a number. Yes?
When do you get the fact that covariance between x and y is equal to p multiplied by
you don't need to put this fact, but I assume this one to be able to calculate this one. You can consider this one as the covariance of the x and y, right? And then if you consider this covariance, it will be a different equation. Is it clear? Okay, cool. We already covered this one. Okay. This image, here I'm trying to show how it looks like if you have a two-dimensional Gaussian random variables. Here, x and y are two random variables. Both are normal random variables, right? So if you look at the 1D of each of them, they are both like bell-shaped, right? So in the first example, the variance of the both of them is 1, and then the covariance is 0, means that they're not related to each other at all, right? And if you look at the 2D, this one, 2D image of the x1 and x2, you see that they're completely circle, right? Shows that they are not dependent to each other, right? In the second one, suppose that you change the variance, right, to 0.7, and the third one you change the variance to 1.5. You see that this slope will be changing as you change the variance of these two. Okay. In this example, it is not necessary that the variance of these two x1 and x2 are same. They can be different, right? So for example, in the second case, the variance of the one in the x1 is 0.6, and the variance of the other one is 1. That's why in the 2D dimension, you see that it is expanded in one direction, but fixed in another direction, right? So looking at the 2D image, you can see, or 3D image, you can see which one has the higher variance comparing to the other one. Another case is here we have the covariance of them, meaning that they're related to each other. It is clear if you look at the 2D image, you see that you can see a slope between them, showing that there is a relationship between x and y. This relationship in this slide is positive. That's why you see a positive slope. If this covariance is negative, you should expect a negative slope between x1 and x2, right? And if you increase this number, you see a sharper slope between x1 and x2. Also, it is possible that the mean of these two random variables, x1 and x2, are not 0, right? So what you expect that having a shift, an offset for the center of this distribution. So for example, here, the shift is in the positive direction in the x1, because x1 is 1.5, x2 is minus 0.5, and the other case for the second example, when you don't have a shift for the x1, but you have a shift for the x2. Basically, the goal of showing these figures to you is that how look of distribution will be changed if you change the variance, if you change the covariance between the random variables, and what happens if you change the mean of these random variables. How does it look like if you want to consider for the lower dimension case? Thank you. Any questions? Cool. Thank you.